Hello, everyone. My name is Olteanu. I would like to thank the ICDT 2022 Test of Time Committee for this award. Jakub, my co-author and former PhD student, and I are very honored by this recognition. This work led to a number of follow-ups in my research team and beyond. These follow-up work span both theory and systems. In this talk, I reflect on some of the main research directions that have been influenced to some extent by our own initial work on factorized databases. This work started with the following paper published in ICDT 2012, Factorized Representations of Query Results, Size, Bounds, and Readability. An extended version of the paper, which strengthened some of the initial results and included their proofs, appeared a few years later in the Transactions of Database Systems journal. This work makes the following two simple observations. First, the relational representation of the answers to a conjunctive query entails a large degree of redundancy due to the way equality joins are defined. Yet this redundancy can be systematically avoided by a succinct and lossless representation, which we call factorized. The term is meant to remind of basic arithmetics where a coefficient common to several terms in a sum can be factored out from all these terms and only multiplied once with the result of the sum. We apply this observation to data, as we will see a bit later in an example. Our initial work also gave effective tools for managing such factorized representations. In particular, it put forward representation systems for factorized answers to conjunctive queries, whose structure is given by partial orders on the variables of the query. We also did this for the provenance polynomial associated with query answers. A second technical contribution was to compute factorized representations that have worst case optimal size. That is, in worst case, one cannot get such representations of asymptotically smaller sizes. Certainly, for specific input databases, one can compute representations of smaller sizes, yet not for all possible input databases. This result was based on a result by Atserias, Grohe, and Marx on worst-case optimal sizes for the relational representation of the answers to joins. We lifted that result to factorizations. Then, we also showed that for joins, such succinct representations can be computed in time proportional to their sizes. So effectively obtaining a worst-case optimal factorized computation of the join answer. This result relies on the worst-case optimal join algorithm leapfrog tri-join by Todd-Velhuizen, and also draws on the seminal POTS 2012 work by Ngo, Porat, Rudra, and Re. Yet very compressed representations are not really useful if we cannot use them further down the processing pipeline. The basic operation that factorized representations support is the enumeration of the tuples in the relation they represent. This enumeration can be done with constant delay, that is, the time it takes to produce the first tuple, as well as the time between two consecutive tuples, is constant in the size of the input database and in the size of the join result. Let us now revisit factorization by means of a simple example. Consider a database of three relations. The relation orders keeps information about customers ordering pizzas on specific days. For instance, Ahmed ordered pizza Basilia on both Thursday and Friday. The relation pizza pairs each type of pizza with its ingredients. For instance, Basilia has garlic, tomato, and mozzarella. Finally, the relation ingredients gives the prices of ingredients used in the different pizzas. Now consider the natural join of these three relations. Part of it is depicted here. As we can see, it entails a lot of redundancy. For instance, all shown tuples have the same customer Ahmed and the same pizza. Other values are also repeated. These repetitions are due to the semantics of the equality join. A natural question is whether we can reduce the number of such repetitions, and what would the natural way to achieve this would be. The answer to this question is actually fairly simple. The join answer is in fact a relational algebra expression built up using the Cartesian product and the union operators over values, or more precisely, singleton relations with one attribute and one tuple. In particular, each tuple is represented as a Cartesian product of singleton relations with one such relation per value in the tuple. Then the query answer is a union of such products. Once we think of the query answer as a relational algebra expression, it is then easy to see that we can simply factor out values of single relations that appear in several Cartesian products in the union. For this, we just need to use the distributivity of the product over the union. This is a law of the semi-ring over the set of all such algebra expressions with the product and union operators. Here is one possible factorization of the join answer. To the left, we have here the structure of this factorization as given by a partial order on the variables in the join query. This structure can be read as follows. We first group by pizza, and for each pizza, we then represent separately the information about the end customer from the information about pizza ingredients and their prices. To the right here, we see the factorization over this variable order. We first have a union of the distinct pizzas, the union of Basilea and Hawaii. For each pizza, we then have a non-materialized Cartesian product of the information about order days and customers and of the information about ingredients and their prices. This is one of the two reasons why factorized representations can be more compact than the relations they represent. The Cartesian products are not explicitly materialized whenever this is possible. The second reason will be exemplified on the next slide. So in other words, this factorization exploits the join dependency in the join answer, or equivalently, the conditional independence in the join answer. Indeed, given pizza, the information about day and customer is independent from the information about pizza ingredients and their prices. It is therefore natural to want to store these two types of data separately and not eagerly materialize their Cartesian product. However, there may be several possible factorizations of the same relation. For instance, instead of first grouping by pizza, we could instead group by day or customer or ingredient or price. They are all equivalent in the sense that they represent the same relation, yet their sizes may differ significantly. Therefore, an important question answered in the original ICDT 2012 paper is which factorizations are asymptotically the smallest possible among all factorizations over variable orders. Yet, we can further compress our factorization. To achieve this, we can refine our variable orders with further conditional independence. We can adorn every variable in the order with the variables that are ancestors in the order and on which it depends. That is, in our example, with which they appear in the same relation. For instance, price only depends on ingredient. Ingredient only depends on pizza, while pizza has no ancestor, so it does not depend on anything in this variable order. This further conditional independence information allows us to observe that the price for an ingredient is independent of pizza, given the ingredient. So if the same ingredient is used for several pizzas, it will come with the same price. We can exploit this insight to represent the price for an ingredient only once. Yeah? In other words, we can cache the price and avoid the repetition. Now, in this example, the saving brought by caching is modest, as the example is simple. Yet it can easily be the case that one can cache large fragments of factorization. In fact, we show that this form of caching can bring asymptotic advantages in factorization size. So now, one question is how factorization, for instance, compares against the common compression techniques like Gzip. For this, we consider the following simple exercise. Create increasingly larger relations in our database example, and then measure the size of the factorization when dumped as plain text, as well as the size of the join answer as file in comma-separated value file format. We then compress both the factorization file and the answer, join answer, comma-separating value files using Gzip with compression level 6, which is a good compromise between speed and compression ratio. And this plot shows the following. The compression ratio of factorization over plain query answer grows as we increase the database size. It reaches 200 times in our experiment. Gzip is not able to identify distance repetitions such as those of entire blocks of rows and columns in join answer. For this reason, its compression ratio of the join answer file remains roughly the same as we increase the database size. This ratio is about 6 times in this experiment. One part of it is due to the binary format of the Gzip output versus the plain text format of the join answer file used as input. For the same reason, Gzip applied to factorization file also yields a compression ratio of about 3 times. Now, in follow-up papers building on factorized databases, we used a range of synthetic and real-world datasets. For instance, the following dataset has been used for experiments to benchmark the performance of various query engines for aggregates over joins. It is a dataset in the retail domain provided by our client of logic blocks. It has one large table keeping the inventory, or 84 million tuples. Here, basically, we store how many inventory units per product, date, and store. And the other dimension tables are relatively much smaller and provide further information on location of stores, store area demographics, and so on. All joins between these tables are key foreign key joins. There is no asymptotic gain brought by factorization of the joins. Yet the joins of such tables still entail redundancy. And why is this the case? Well, each tuple in the table inventory needs to be expanded with information from the other tables. So the same information will appear in many of these tuples. We look at compression factors brought by factorization of the answers of the 2 natural joins in our examples here, as shown on the slide. The compression ratios are non-trivial, about 26 times in one case and almost 160 times in the other. In our works, this improvement factor carries over to computation done over the factorized joins. So to summarize this, why are factorized representations useful? The short answer is that they give a proper balance between succinctness and efficiency of subsequent processing. For one, they are lossless, so they can represent the same tuples as in the plain relation, yet they can be much smaller. The major technical result here is the characterization of the sizes of factorized representations of the answers to any conjunctive query by the fractional hypertree width of the query. This considers a generalization of this width measure from Boolean to conjunctive queries. In the particular case of alpha-acyclic conjunctive queries, there are factorized representations whose sizes are linear in the size of the input database. As already mentioned before, they also admit enumeration with constant delay. This is effectively as good as enumerating from a list of tuples, like from a plain relation. The fast enumeration applies to both the monomials in the provenance polynomial of a query answer and to the tuples in the query answer. Now, constant delay enumeration is prerequisite for more complex computations in the factorized domain, such as, for instance, aggregates. It turns out that aggregates with group by clauses and even training machine learning models can be performed directly on factorized representations of join answers. Good. So far, we have mentioned several benefits of factorizations as observed in our own work. Have such benefits been reported by other researchers in their own works? Are other researchers using or improving on aspects of factorizations introduced by our work? Or stated simply, is there any impact case that can be made for this work? And next, I will give a brief account of some works that have been influenced by our ICDT 2012 paper. In our investigation for such works, we realized that factorized database ideas have been subsequently used in research and development in both database systems and database theory. While we expected to find such works in database theory, we were particularly pleased to see their influence on systems building efforts. Furthermore, it is remarkable that these subsequent works are very recent. So we were able to identify the following broad topics where factorized databases have been used. One in graph data representation and processing, then in enumeration, in static and dynamic query evaluation, for query provenance management, for factorized aggregates, and for factorized machine learning. In the following, I will highlight a few of these works per topic. One area where factorizations are used is graph data systems. The underlying observation there is that graph traversals call for joins with large outputs that factorize very well, unsurprisingly. Indeed, factorizations are particularly beneficial for many-to-many joins, such as joins used on the edge relations to express hops in a graph. I would mention 4 distinct and very recent works that use this idea. In their recent VLDB paper, Salioglu et al. Are building a graph database management system where data is kept in a factorized representation so as to avoid repetitions. In their recent Sigmund paper on parallel computation of SQL queries, Smagulova and Deutsch use a factorized representation of intermediate results that are shipped between the compute nodes. They can then compute aggregates directly over factorized data. Wu et al. Developed a method that represents the homomorphisms from the given query pattern to the data graph in a compact form that, as they say, is similar to factorized representations of query results. Jakub et al. Also use a similar factorized answer graph for Sparkle conjunctive queries. They conclude that while factorization is sometimes a significant win for evaluating relational queries, it is virtually always a win for evaluating graph conjunctive queries. A second area where factorizations are used is the enumeration of query answers, where the enumeration can now be in a desired order or used for ranking. Furthermore, it has been investigated in both the static and dynamic query evaluation setting. So in ICDT 2017, Amarilli et al. Strengthened the enumeration result in factorized databases to more general circuits called deterministic decomposable negation normal form circuits, which are used extensively in an area of AI called knowledge compilation. In ICDT last year, Shalin Deep, Xiao Hu, and Paris Kutris investigate the enumeration problem for conjunctive queries, and as they state, their approach builds upon the idea of factorized representation and show that for certain access patterns, it is possible to improve the space requirement while maintaining the constant delay enumeration. Now, in VLDB 2020, Tsiavelis et al. Generalized the enumeration approach for factorized representations to ranking the answers based on some monotone function. In the same spirit, Carnilli et al. Investigate in their post paper last year the problem of direct access to ranked answers to conjunctive queries. The goal is to define a syntactic characterization of those conjunctive queries that admit linear time preprocessing followed by constant delay, direct access to any answer in a given ranked order. They say that their work is part of a bigger challenge that continues the line of research on factorized databases, and in particular look for compact and efficiently computable representations of query answers while remaining useful to downstream operations. In the dynamic case, Bergholz, Keppeler, and Schweikart give a dichotomy for dynamic query evaluation. They state that a specific class of conjunctive queries called Q-hierarchical is the maximal class that admits single tuple updates, that is both inserts and deletes, with constant update time and constant enumeration delay. All other conjunctive queries cannot achieve both these constant times. The data structure that allows for such an efficient updates and enumeration is a factorization, as introduced in our initial work. In our own work on dynamic query evaluation in Sigmund, we leverage factorization for the representation of query answers, data updates, and the materialization of intermediate results. This led to the FIVM system, which is built on top of DB Toaster and is available in the public domain. Again, in our own work, this time in pods, we proposed an approach that can trade off between the time to compute the factorized representation of the query answer, the time to update it under inserts and deletes, and the time to enumerate the tuples in the answer. This approach recovers many prior results for static and dynamic query evaluation. Okay, a third area where factorization proved useful is the management of query provenance. In our initial ICDT 2012 paper, we apply factorization to the provenance polynomial of a conjunctive query. Now, Lee, Ludesher, and Glavik build a PUG system to support why and why not explanations for query answers. As they say, this system utilizes factorized database techniques. In an awarded VLDB paper, Daniel Deutsch and his collaborators propose a natural language interface for formulating database queries. The answer system they propose is essentially based on the factorization of the query provenance, which is adjusted to their need. Okay, so now, as it removes redundancy in the representation and computation of joins, factorization is also useful for the efficient computation of aggregates over these joins. This is the main message of our follow-up work in VLDB. This led, in fact, to a new low complexity for the evaluation of aggregates with group by clauses. This has been acknowledged in several seminal works, in particular in the awarded POTS paper on functional aggregate queries by Abokamis, Ngo, and Rudra. They say there is much in common between factorized aggregate computation and the inside-out algorithm in the case of computation over a single semi-array. In particular, they have the same runtime complexity. They are both dynamic programming algorithms, whereas factorized computation proceeds top-down, inside-out proceeds bottom-up. The same intuition has been provided in the works of Chris Ray in the AJAR paper, also in post 2012, and later in their empty-headed system published in Sigmod and later in TODS. Very recently, Eugene Wu and his students are working on a system that uses factorization for matrix representation and processing. And the best newcomer paper awarded at this ICDT by Capelli et al. Shows that linear programs over joins can be factorized and therefore solved much more efficiently than over the materialized join result. Now, the final area that I want to briefly mention is that of factorized machine learning. The reasoning goes as follows. The data-intensive computation for training machine learning models over relational data can be expressed by a batch of aggregates. Therefore, by leveraging the body of work on factorized aggregate computation, we can now readily provide efficient model training over relational databases. First off, the term factorized learning has been proposed by Kumar, Norton, and Patel in a Sigmod paper. They say, we call our technique factorized learning, borrowing the terminology from factorized databases. This line of work effectively extends the general idea of factorized computation to machine learning algorithms over joins. This also includes our own work with the fantastic folks at Relational AI, where we looked at a variety of models to be trained in a factorized way, such as, for instance, polynomial regression, factorization machines, principal component analysis, support vector machines, k-means clustering, and others. We published this work in a series of papers in PODS, Sigmod, AI Stats, UPSLA, and others. We also released several prototypes in the public domain. Okay, now we reached the end. I would like to wrap up by advertising an upcoming workshop on factorized databases. It will take place in Zurich at the beginning of August. It will be both on site and online. The topics of the workshop have been summarized in this talk, and several of the works mentioned here will be discussed there. In case you'd like to attend, please contact me. Thank you for listening.